Okay guys, so what we're going to talk about in this video are Kirchhoff's laws, right? So these are just a set of rules that we can add into our toolbox for circuits that help us to um, actually solve for the current that is flowing in circuits in a little bit more of a complex way, but it also lets us down the line solve more complex problems. So this is a good thing for us to have. So there are basically two rules that I want to go over with you. The first one here is that if there's a junction in a circuit, then all the current going into that junction has to come out, right? So for an example here I've drawn here on the side, if we have this line of current, there's some current coming in here, and there's some current coming in here from I2, that has to be equal to the amount that's coming out. So this is kind of like a conservation of energy sort of check, but for current, right? It makes sense. Whatever you put in from these sides has to come out. So this is sort of intuitive for us to know, but where this comes in really in handy would be, let's say if there are a lot more wires coming into a junction, and then some of them have current coming out. Like let's say here I have an I4, and then here maybe I have an I5 also coming out, and then some of them also have current coming in, I6. You know, circuits can get super complicated. And let's say this junction happens at all these wires. So this is just an easy way to summarize all the current that's coming in and coming out. And the way we would do that here is we would take everything that's coming in, so all the arrows pointing towards our junction. In this case would be I1, and I2 is pointing in, and I6 here is pointing in. So that takes care of everything coming in. And then that's going to be equal to everything that's going out. For us, this is going to be I4 is going out, I3 I see is going out, and I5 is going out. So sorry, these are out of order. But so you can see here that this is a nice way to set up kind of everything that is going in and out of a junction, right? So our second rule here is also something that we've already kind of covered. We just want to give a little bit more context to it, and this helps us out for some really complex circuits. Is that if we have a loop, that means a closed loop. So any sort of closed loop like this where you have essentially four corners connected, you could say, you know, my battery is part of this loop, right? So any wire that makes a loop, the total voltage over that loop has to be zero. This is sort of another, if we kind of think of this as conservation of energy, it might make a little more sense here. So basically the way that we do this is that anything that is a voltage source is going to add to my loop, right? Or it can add to my loop. And then everything that is a resistor subtracts from my loop. Now, I just put this sort of as just guidelines because these sources and drops can be positive or negative depending on the direction of the current, right? So let's say in this example right here, I have a positive terminal and a negative terminal, right? So if I'm going right here from negative to positive, what I'm doing is I'm gaining potential, right? Really on our battery here, we'd say this is something like 0, and then this is some positive voltage, or it'd be like 50 volts or 10 volts, whatever it is. So when we cross this way, going to the left on this part of our wire, we are gaining potential. Here we have low potential, here we have high potential, right? So that's what I mean by it adds to our loop, okay? But then anytime we go across one of these resistors, our potential is going down, right? So the direction really matters here. I'll get to that in a little bit. But the way that people usually define this is not by starting and ending at the battery, because that can get a little bit confusing, but starting and ending at each corner, okay? Starting and ending at each one of these corners. Let's say we start from this corner right here. This is our home base. okay? And then we go, okay, across this resistor, and we're saying our current is going this way, okay? So we have some I1 traveling this way. That current will still keep traveling this way, and this is still going to be, I1 has to be the same. Okay, these are all in series, and then this still I1. But then when we go this way, we are adding, right? So the way this will look for this summation right here would be, in this case, whatever my voltage is. So this would be the part that I add in, minus I1 R1, minus I1 R2, minus I1 R3. And then, so we've talked about this already, where we have to drop our entire voltage when we complete our loop. We can't have some extra voltage. Like, I can't start with 10 volts here, but somehow drop 12 volts, right? I don't have enough voltage to do that. But also, it can't be less. It can't be more, and it can't be less. So that means if I have a 10-volt battery, I have to drop those 10 volts across my entire loop. Okay? I can't drop only 8 volts and be like, oh, I saved a little bit. No, so it still has to drop over the entire loop. So all of these things, when we add them all up together, have to equal to 0. Okay? So the way we usually do this is we get all of our resistors here on one side, so that it would be my V is equal to I1 R1 plus R2 plus R3. And you can see all we've done here is we've reconstructed V is equal to IR, where all of my resistors here are added up because they're in series, right? So this is just another perspective on what we've already been looking at. So here's just a few things for us to keep in mind here. Are the direction that we're looping, right? We can also loop the other way. So that would be kind of weird in this situation, but sometimes we need to do this. If I start from home and I loop this way, I can do that. Definitely I can do this. So it's just when I travel the opposite way here, all of my resistors are going to be positive and my battery is actually going to be negative. Because when I go across my battery, I'm going from high to low. Okay, so I'm losing voltage, but then I'm gaining it over these resistors, right? So here is just a little guideline where if you're crossing a resistor and you're going in the same direction as the current, you put it as negative IR. If you're going in the opposite direction, it's positive IR, right? And then here, if you're going from negative to positive across a battery, we have positive voltage. And then, of course, going in the opposite direction from high to low, this is negative voltage. So this is just a good thing for us to keep in mind, right? For those really complex circuit situations. And then I want to do a simple example, one that you guys can confirm with the previous rules that we've gone through before for series and parallel. Okay, so I have a circuit here that is fairly simple. It has a resistor and then 2 resistors in parallel, right? So just so you guys know, what we can do with Kirchhoff's laws is really, really deep. So we can go with like multiple power sources, and we can have all sorts of crazy things in our circuit. And as long as we follow these rules, we can actually start to solve for the current that goes throughout my circuit, and the effective voltage, these sorts of things. Okay. So what I've done here, just to kind of clean up my time instead of writing down all the math. So I have to write kind of slowly to make my handwriting a little bit better. So I've done this beforehand here. There are 3 things here that we can gain by using Kirchhoff's laws on this circuit. The first one is our loop rule, right? So our loop rule says, let's say I start from this corner right here. This is my home. And then I go all the way across this way in this loop. Okay, so when I do that, I have to use this Kirchhoff's second law that says that this whole loop has to equal to 0, right? So that means my, so I have V, so actually I'll go ahead and put this as my 10 volts, minus I1 R1, minus I2 R2, Okay, this is equal to 0. So when you sum all of these things together, it has to equal 0. So all I did is I went across the battery, 10 volts, went across resistor 1, took away a little bit, went across resistor 2, took away the rest, should be 0, right? Okay, the other thing is that we can make a loop right here. We can make another loop, okay? But there's something for us to keep in mind here, okay? The thing that we need to keep in mind is that when my current goes this way throughout my circuit, it has to branch off from this direction, right? So our current has to keep flowing this way and this way at this junction, right? We know this. So my current should actually flow downwards here, but that's going to be against the direction that we're using for our loop. Our loop here, this clockwise loop, is going to be against resistor 2. It's going to be against the direction. So we're going to have to use these little rules that we just showed right now. Specifically, we're going to have to use this one right here, where we're going in the opposite direction of our current. Okay, but thankfully, our current direction here for R3 is the same. Okay, so this works out the same. So the way we'll do this here, and I'll go ahead and do this actually in red, is all I have here is I3 R3 minus I2 R2. Those are the only two things I have in this little loop. I don't have a battery, so these two things have to equal to 0. Okay, so this will be my second formula that I have. And then the third one here, I can use that I have a junction right here, so I can take advantage of this. And I can say that my I1, what that's going in, and here I have, I want to have I2 going towards resistor 2 and I3 going towards resistor 3. So this junction right here, I can describe with the junction rule, so that I1, whatever's going in, is equal to whatever's coming out, which is I2 or I3. Okay? So what we have here, so it's going to look a little bit messy, guys. So compared to the method we've been using before, this might look messy, but, you know, having this in our toolkit is really important down the line. So what I've done here is I've just shuffled these formulas around a little bit. Okay? So I have this formula right here for equation 1. All I did is I put the 10 volts on the other side. And then right here, I have the same formula as before, only I've switched it around, right? So the 0 is on the left-hand side. And then what I want to do is I actually want to solve for one of these, because right now I have a system of equations. I have 3 formulas, and I have 3 unknown variables. I have I1, I2, and I3. So this is good. I have 3 formulas, 3 variables. You can use this system of equations in order to find out what each current is. It could get a little messy, but it can be done. That's the important thing here. Okay? So in this case, what I've done is, then, you know, there's a lot of clever ways that we can do this in matrix. I've just gone ahead and done this, you know, in the most straightforward way, I think. So I set I2 is equal to I3, and then I solve for I3. So here I have a value for I3, okay? And I'm going to plug in this value for I3 right here. So this expression, when I replace I3 with I2 R2 over R3, becomes this right here, okay? And then now we can get rid of I1 by plugging this whole thing right here, that's just in terms of I2, into our first formula. Okay, so here I've gotten rid of I1. So first I got rid of I3 by turning it into I2 in terms of I2, and then I got rid of I1 by turning it in terms of I2. So putting all of this together, I have one formula, which is our original equation 1, except now it's completely in terms of I2. So using this, we have here, factoring out I2, getting all of our resistance terms together, plugging in our resistor 1, 2, and 3 values that we have. We had them up here, 2 ohms, 5 ohms, 10 ohms. Okay, so go and plug these things in. And then solve essentially my V is equal to IR function. You can see that's what it ends up being. And I get the current going through resistor 2 is 1.25 amps. Great. Now that I have that, you can start to work backwards. Well, if I know I2, I can plug this in here and figure out what I1 is, right? And I can figure out here what I3 is, right? So here in this case, I went first to figure out I3. So just plugging in my 1.25 here with my resistor values gives me back I3. Okay, and sort of this avalanche effect. Now we know all of these things. I can go back and use my junction rule, just plug in I2 and I3 and get I1, right? So now I've figured out all three of my current values for my resistors by using Kirchhoff's laws, right? So again, this seems like it could seem like a much messier version of the rules we were using before for series and parallel, but these don't require us to break this down into some equivalent resistance, which we might not always be able to easily do. But it does allow us to scale up to more complex circuits, right? So here we found all three of our current values.